Okay, thanks everyone, and thanks Chris for the introduction. So yes, I'm going to be talking about quantum physics today, and it's quite an exciting time for doing research in quantum physics, even though this is a subject that started now over 100 years ago with Einstein first posing some ideas. 100 years old and well developed for some time, but it's only right now that we're starting to do a new range of experiments that are really putting to the test some of the wacky, crazy ideas that quantum mechanics seems to predict for the very, very small particles that make up the universe, putting those things to the test and seeing some of these weird effects appear in reality. Not only taking those weird effects as going, oh, that's sort of cool, I'm interested in looking at that, also thinking about how can we use this, how can we do exciting new things with these weird quantum effects. So that's what I'm going to talk about today, is try to give you a flavor about what is quantum mechanics and why is it interesting, but also what does it tell us about new technologies such as quantum computers and cryptography and things like that. Okay? So I know it's first thing in the morning, and it's always good to start off with a puzzle. Maybe some of you have seen this puzzle before. It's an old puzzle. But let's see if we can come up with some solutions and get your brains working. So imagine you have two rooms. You can be in one room or the other room. When you're in one room, you can't see what's going on in the other room. One room has 3 light switches, and they're hooked up to 3 light bulbs in the other room. And you have to figure out which light switch matches up with which light bulb. And of course, we all do that by testing all the switches on the wall and see what goes on and off until we find the right one. But there's a trick here that makes it quite hard, is you're only allowed to go into each room once. You can go into the switch room once, and you can go into the bulb room once, and that's it. And you want to try to figure out which switch is hooked up with which bulb. Now, I'm going to give you just 30 seconds. Talk with your neighbor and see if you can come up with an answer before we talk about how you could do this. You have an answer or a question? Okay. Okay, so this is good. I see lots of hands going up. So actually put up your hand if you think you've got an answer to this one. How many people think that there is no answer? There's no solution to this problem? Well, a few people. So we could pose this as a mathematical problem. Think about some set of wires that connect each switch to each bulb, and think about which way could you set those switches such that you walk into the bulb room and you can see which ones are connected to which. As a mathematical problem, this has no solution. There's no way we can set the switches in one room, 1 on, 2 off, 2 on, 1 off, such that when we go in the other room, we can work out a one-to-one matching between those two things just by looking at the lights. Okay? But I did see lots of hands up. So maybe some of you think, well, there is a solution if I think a bit more broadly. So how about we have another hand up? You can propose one.
You turn 2 switches on, then turn 1 off, then the switch that's still on has a bulb on and that's connected. The switch that you never touched is still dark. That bulb is still dark, and so they're 2 connected. And the bulb that's hot is the one that you turned on and off again.
The one that's hot but off, that's the one you turned on and then off, and you could match up all 3. So it's actually only one of many solutions. Many of you might have another one. It involves thinking a bit beyond just the single parameters of a switch is connected to a bulb, and there's only one thing I can learn about that. This is the one you propose is my favorite solution because it's a nice physics solution. It uses a little bit about thermodynamics and so on to figure out how these things are matched up. So maybe it's a bit unfair to mathematicians to say this is a physicist solution. I think it's just a smart solution, a good solution, a solution to the problem that involves thinking a bit more broadly about what a switch is and what a bulb is rather than just posing it as a restricted mathematical problem. Okay? And I like to think that the type of thing we're doing now in quantum mechanics, which is applying concepts of information to quantum mechanics, is very much along the lines of the way we just thought through the solution of that problem. So when we think of information, such as what a computer processes, what we send over optical fibers when we communicate from one country to another, all of the things that we see or hear or experience on the internet and so on, all of this stuff that's information, we can sort of think that it lives in this abstract mathematical world of ones and zeros and numbers, but in reality, information is always associated with some sort of physical object, whether it's the little bits of a magnet in a hard drive or the little electrical switches in a computer transistor, or even just the placement of ink on a page when you talk about the information in a book. Information is physical, it's subjected to the laws of physics, and the best framework we have, and I'm going to talk more about this in the first part of this talk, the best framework we have for dealing with physical problems is quantum mechanics. Well, we should think about combining the ideas we've learned about quantum mechanics from Einstein and those who followed together with thinking about information, and this has led to a new area of research called quantum information. Sometimes called quantum computing because that's the most direct and specific application of quantum information, is thinking about how do we store, manipulate, process, transmit information, but thinking about it as a physics problem rather than as a mathematics problem. What types of limits do the laws of physics put on information processing? But also, what type of new opportunities maybe? And let us solve that problem of the light bulbs and the switches in a way that restricting it to a mathematical problem didn't let us solve. It said there was no solution, but there was a solution. Can we somehow take that idea, that trick we used to solve that problem, and make it very general and think very broadly about what types of things can we do in our universe? It's obeyed by quantum mechanics, and but we want to think about it as an information processing world. And that's really what we're going to talk about today. Okay, but before we get into the details of what quantum mechanics says about information, let's talk a bit about quantum mechanics. And it's unfortunate I can't do with you guys what I do with all of our undergrads here, which is teach them 4 years of quantum mechanics, a few hundred lectures all up, lots of assignments and exams and problems where you really get immersed into what this field is and how strange and exciting it is, how much it tells us about our universe, and how much we still don't understand about it. But I'm going to try to give you a hint about what this weird world of quantum mechanics or quantum physics is. Okay, so first of all, before I say what it is, let me tell you about how great it is. This is one of the greatest achievements, I think, of modern thinking. Okay? Quantum mechanics has superseded all of the physics that was developed in the time of Newton, or going on to electromagnetism, Maxwell, going on to thermal physics, talking about Kelvin and other famous physicists in the past. Those are all classical physicists from our perspective, and when we say a classical physicist, we mean non-quantum. Quantum is what's taken over all of physics and describes just about everything we know. And I say just about, there's a little asterisk up there at the top that says just about everything. Well, it hasn't quite managed to describe gravity yet. There's all sorts of problems with describing gravity in quantum mechanics. And unfortunately, we're not going to have time to talk about those problems. They're perhaps some of the most interesting ones. But aside from that, okay, that's a big if, it's a big but aside from that, we can describe just about everything else with quantum mechanics. And so we really think of quantum mechanics as a framework for physical theories. We have theories to describe, solids, liquids, gases, metals, all sorts of different states of matter. All of those things now are developed as quantum theories, and we think of them as describing the quantum mechanics of the particles that make them up. Lasers, hard drive, LEDs, the way that electrons behave in semiconductors that have allowed us to develop computer chips and other types of technologies. The very fundamental interaction of light and matter, that's all described quantum mechanically, how atoms absorb and emit photons. Chemistry and chemical reactions, underlying everything in chemistry is really physics, and all of that physics is quantum mechanics. Chemists use just a part of quantum mechanics to do everything that they do. Getting down to the smaller scale, when we talk about nuclear structure and what's the form of the nucleus, that's all quantum mechanics. You go down deeper into the subatomic particles and all of these strange, exciting things I think you've already heard about with the search for the Higgs boson and so on. All of that, all of those things are quantum mechanical theories. And then finally going to the grandest scale, sometimes people say quantum mechanics describes only the very small, but it also describes things on a very large scale when we get to extreme conditions such as those seen in the very early universe. So if you want to figure out what happened after the Big Bang, you need quantum mechanics. What you really need is a quantum theory of gravity, which we're still working on. But quantum is used in cosmology all the time now to describe how the universe formed and so on. So it's a framework that really describes just about everything in modern physics, and that's why we spend so many years teaching our undergrads quantum mechanics, is because it's just so fundamental and applies to everything. Okay, so that's what it's good for, but I haven't told you at all what it is. Well, those of you who have read some things about quantum mechanics, if you've read anything about quantum mechanics, you've probably heard right in the first sentence, right on page 1, quantum mechanics is weird. It predicts all sorts of strange things that we think of initially as nonsensical. Now, it's not weird in the sense of, well, I find when I look at a Picasso painting, I'm like, oh, what's going on? There's like shapes and stuff. It's all sort of weird but nonsensical to me. Quantum mechanics has this internal logic to it. It's completely consistent. There's nothing nonsensical so much as weird as in, well, it's completely against our intuition. You might think something is one way, but you find it's quite different. And there's a logic to it, there's a reason to it, it's just not the way you thought it was going to be. And just some examples of the types of things that are so weird about quantum mechanics. We're going through a list. These are all the things that we tell students in their very first year of university. Maybe even you've come across some of these things in high school, but then we spend years after years after we tell them about how weird this is, trying to figure out why is it that weird. And we've only partially come up with some of those answers. So we have things like, well, we can't talk about an object having both a position, where it is, and also a momentum or a speed, how fast is it going, at the same time. We can talk about one or the other, but not both. Why is that? That's what quantum mechanics says. This idea of complementarity, that waves behave as particles, particles behave as waves. What does that mean? We spend years trying to sort out what that means. It means something very precise mathematically, but what does that mean for what's out there in the universe? Well, that's a much trickier question. And just looking at these particles and waves will affect their motion. You can't observe something without affecting it. Now, something that captures some of these very weird ideas is that of Schrodinger's cat. I even have a separate slide on that. This is what Schrödinger, one of the founders of quantum mechanics, used as an example to just show how ridiculous quantum was. He didn't want to sort of jar people into thinking, oh yeah, this is what quantum mechanics is saying. He wanted to show people just how nonsensical and against classical intuition it would be if you applied it to everyday objects. He says, well, imagine I set up this actually horrific experiment where, okay, reading through it, step one, I have just a single atom of a radioactive material. And at any given moment, it can decay, or maybe it won't decay. This is a single atom, a single nucleus. It's described by quantum mechanics, and we have a very good understanding of how that quantum mechanics works and how we describe this decay process. And at this certain time, when there's a 50-50 chance, we describe this single nucleus mathematically by saying, well, it's both decayed and it hasn't at the same time. Okay? Quantum mechanics says that's the way you describe things, that they're in this quantum superposition, they have decayed and they haven't at the same time. Now that sounds quite strange, but that's the type of thing we're used to when dealing with things like single particles like atoms and nuclei in quantum mechanics. But Schrödinger said, let's take this and bring it to the real world and see what that would mean. Well, if it decays or doesn't at a given time, step two is, well, we have this thing right next to a Geiger counter that will go click or not, depending on whether it's decayed or not. And that whether that Geiger counter goes click, it'll drop a hammer or it won't, and break a vial of poison or not. And that vial of poison, if it's broken, is going to kill this poor cat sitting next to it. But if it doesn't, if that atom doesn't decay, the Geiger counter doesn't go off, the hammer doesn't break, and the hammer doesn't fall, the poison doesn't escape, the cat doesn't die. So these two options, and we have no problem in the real world thinking about something happening or not. The cat is alive or the cat is dead. But this weird quantum mechanics of describing a single atom, of saying it's both decayed and it hasn't at the same time, it's in this weird quantum superposition, has suddenly gone through a chain reaction to say that this cat is both alive and dead at the same time. And it's just, this is the weirdness of quantum mechanics. People say, well, I could accept it maybe for an atom, that there's odd rules that describe how it works. For a nucleus, there's these odd rules. But for this cat being alive or dead, it just seems weird and nonsensical. We're going to come back to Schrödinger's cat as we get further into the idea of quantum computers. So I wasn't done my list, though. We have things like quantum tunneling, because a particle, if it's moving, doesn't have to be located in a specific spot. If it's located in a specific spot, we don't know how fast it's moving, can lead to situations where we can trap a particle, and then you go to look for it and it's gone. It's just, we say it's tunneled. It's just magically appeared outside of our trap. And then something I'm not going to have really any time to talk about, but people consider one of the biggest mysteries of quantum mechanics, is how not a single particle, but two quantum particles can be related in a very strange way, such that looking at one particle can affect what the other particle is doing, even if it's on the other side of the universe. All of these weird things about quantum mechanics just don't seem to make sense. When we first present them, we tell our students, oh, look at all these weird phenomena. They don't make any sense. But then we start to develop a mathematical formalism, a framework. We start to show how it makes the right predictions for atoms. It makes the right predictions for nuclear physics and for subatomic physics. It makes the right predictions for describing gases and solids and electrons and semiconductors. It allows us to understand chemistry and so on. This mathematical framework is beautiful in its predictive power, but at the heart of it are these mysteries which just seem incomprehensible. So follow the rules and it all works, but what does it all mean? So this is precisely the type of thing that really bothered Einstein. So we could ask some questions. Well, quantum mechanics is great at explaining all of these things, but what does it fundamentally mean? And some people say this is a bit like, well, you can have a car and drive it and have no idea how it works. Okay? And most people do. But as scientists, we find that a bit unsatisfactory. I want to know, how does that car work? Okay? I pour this petrol into the car, and then I press this lever, and I'm moving forward. Okay? That's all I need to know to drive the car. But why does it do that? What's going on under the hood? There's an engine, and how does that engine work? And why can't it go faster? Why does it need this fuel? How could I make it run cheaper or cleaner or something like that? I want to answer those questions. And that's the same approach that we should take to quantum mechanics. Don't just use it. Don't just say, well, the mathematical formalism works. It's weird, but you don't need to understand why it's weird. I want to understand why it's weird. I want to understand what's going on. We think we need to answer these types of questions in order to figure out this final elusive step of the puzzle, which is how do we apply quantum mechanics to gravity? I won't say anything about that idea of measurements, but really these are the questions that Einstein was asking about. He really didn't like the quantum mechanics that he helped develop. He said, okay, fine, it's good as a formalism, but there must be something more to it. There's something that we're not quite understanding. And if we want to actually take all of these new developments in physics and ways of controlling systems at the quantum level and do things with it, sort of make technologies for the next 100 years, just as it's helped us make technologies for the last 100 years, I think we need to answer these questions. I think we need to know what's going on underneath the hood and say, we understand quantum mechanics and now we can see how to use it better. Let's take up the challenge. Okay. And so this is really this new area of quantum information, this idea of thinking about quantum mechanics as a language for describing information processing in the physical world. Thinking of quantum mechanics as the language for describing computers and communications and things like that. I think it's helping us get a grip on this question. It's helping us understand some of this quantum weirdness that's eluded people for so long. And I'm going to try to convince you of that with a few examples for the remainder of this lecture. Okay. So that's the end of this introduction to quantum physics. It's very unsatisfactory because I've just told you just how weird it is. I've sort of motivated, we want to understand why it's so weird. Now we're going to talk about a specific idea of quantum computing that's hopefully going to reveal some of these answers. Okay, so to talk about quantum computing, I'm going to motivate things with a problem that's hard for computers. Okay, we can think about it as the type of problem that a computer should be able to solve, but one that it actually finds quite tricky. And this is going to be a bit like that problem we talked about right at the beginning of the lecture with the switches and the light bulbs, one where it looks like it's going to be impossible to solve, and then we find a physical solution, and then now we're going to try to understand why that is. Okay, so everybody's heard about factoring, right? So that is, take a number and try to figure out if we can write that number as the product of smaller numbers, integers. What are the prime factors of a number? This is actually quite a hard problem for computers. And that's especially true if you take a big number that's the product of just 2 primes, okay? Rather than a whole bunch of smaller primes, the product of 2 big primes. So let me give you some examples. So 4,333, I've given you the answer of how to factor that number. It's the product of those 2 prime numbers, 41 and 113. Now, if you sat down, if I just gave you the number 4,633 and asked you to factor it, what might you do?
Go through one by one.
Go through one by one. Yeah, with prime numbers. So you say, okay, can I divide it by 2? Well, clearly no. It's not an even number. Can I divide it by 3? It might initially look like it, but you check, nope. So don't need to try 4, that's not prime. Try 5, try 7, try 9, or nope, don't need 9. Try 11. And playing with this might take you a while. Eventually you get up to 41, and you're like, oh, it's a bit unlucky it took this long. But you divide it by 41, you find 113. You're like, okay, that's one divisor. And 113, you could check its prime, and you're like, okay, I'm done. So that doesn't sound very efficient, maybe. It takes you a long time on a calculator, but that's pretty much the best we can do in terms of if I had to write a computer program that's going to do this for me, I could write that. That's pretty much the best we have. Okay, here's a trickier one. If you guys can see that. So what's on the top line, there's these two very close lines. What's on the top line is a 129-digit number. It's a special number that was given a name, RSA 129, by 3 guys with the initials RSA. They put this out there in 1977. They just put that top line out there in the mathematical literature and said, I challenge you to factor this number. They didn't tell us what's written underneath. I hope you guys can see that, is basically a 65-digit number and like another 65-digit number. And those are prime numbers. The top line is the product of those 2 prime numbers below. So they put this out there in 1977 without telling people the factors, and they said, go ahead and factor it. I have to look ahead to see when it was actually done. Yeah, it took 17 years. Okay. Now it wasn't that someone at the time said, okay, I'm gonna take my computer and start the algorithm of just, okay, check 2, check 3, check 5, go on through all the lists before we get up to that solution. If they had done that in 1977, that computer would still be going. So they didn't even try. They waited, and then around in the early 90s, they started to network computers together. It was the early days of computer networking in the internet. And a group of mathematicians at different universities linked their computers up together using an early form of the internet and got them to work together in checking more and more prime numbers and collaboratively using, at the time, most of the computing power on the Earth. They did it in 8 months. If you had to get your computer to do that now, it wouldn't do it very quickly, but it certainly could do it now in a matter of days. Okay? But that's a hard problem. Okay? And in fact, most of the internet security that we have at the moment is based precisely around that being a hard problem. This name RSA, you may have heard of it before. It is the method of encryption you use when you get on to the internet in your web browser. When you say, okay, it's secure, so I can put in my credit card or something, it's using a particular encryption protocol that is based around the fact that factoring numbers is hard. It's based around the fact that factoring this 129-digit number takes a long time. Now, as I said, your computer now could factor that number in a matter of days. So that's not very secure, but all they have to do is say, well, we don't have to stop at a 129-digit number. Let's use 256-digit numbers. Or let's use 1,000-digit numbers. Because as we make that problem bigger and bigger, the computers just fall apart. It takes, as we make that number just a bit bigger, the difficulty of that problem is growing exponentially in the size of that number. So here's an example. So right now, if we tried to make an encryption problem based on factoring a 300-digit number, And I haven't given you an example, but it's very easy to write a little program that comes up with 300-digit numbers that are the products of primes. It's very easy to come up with examples. If I use a 300-digit number, if I had a terahertz computer right now, and I don't, it would take 150,000 years to factor that number. That's a hard problem for a computer. This is so hard that you can basically, for all intents and purposes, say that's an impossible problem for a computer. If it's going to take 150,000 years, well, we make it a bit longer, make it take 10 billion years, and you say, I don't even know if the universe is going to last that long. Okay? You can basically say that's an impossible problem. There's no solution. But maybe we're saying there's no solution in the same naive sense that with the 3 switches and the 3 light bulbs, you said, well, there's no solution. In 1995, this guy, Peter Shor, who was working at IBM at the time, said, imagine I built my computer, not the way we normally build it now, but in a very similar way, but using quantum mechanical rules. Okay? So I'm going to have, instead of the bits in my computer, I'm going to use quantum systems that are like bits. I'm just going to interact them with gates. I'm going to have some logic gates, and I put those logic gates together. And I think, how hard would this problem be for such a quantum computer? And he showed that it's not very hard at all. Now, I'm not going to give you the details of this, because we'd have to learn quantum mechanics first, and then work through the gory details of this algorithm. It's all based on something called a quantum version of a Fourier transform. The point is you can work through, count how many steps this quantum computer would take to solve this problem, and it turns out to be nice and efficient. So, as an example, with this 300-digit number that would take 150,000 years on a terahertz computer built using classical rules, built like every computer we have nowadays, if I ran this on a comparable speed, i.e. terahertz quantum computer, that it would be able to factor that number in less than a second. And whereas if I wanted to make the problem harder for the classical computer, make it take 10 billion years, I only have to grow the length of that number a bit. Instead of using a 300-digit number, maybe use a 400-digit number. That 400-digit number on the quantum computer would still take, well, maybe it now takes a second. But it's not going to grow exponentially with the size of the problem. It actually just grows nice. It's actually like a quadratic function. So suddenly, that problem that was, for all intents and purposes, impossible becomes doable if we use quantum rules. I wish I could give you a good, simple understanding of why that is. If I had one myself, I'd probably get the Nobel Prize. Nobody really understands why quantum systems are able to do this, but we can show that they can. We can use the mathematical framework to see that they can, and that really makes us say, well, why is this? Here's a new handle on understanding some of this weirdness of quantum mechanics, because instead of talking about particles being in, here or there at the same time, or instead of talking about cats being alive or dead, I can now frame this in the language of a computer problem, and I can ask very specific questions like, how does the difficulty of this problem scale with the size of the problem? Very specific scientific questions that I can now say, okay, let's look for generalizations of this. Let's look for theorems that describe why this should work. Let's approach this scientifically. So from a theorist point of view, I'm a theorist. I think abstractly about things and think about why they are the way they are. That's the way I would approach things. But some of my colleagues who are experimental physicists think that's awesome. I want to build one. And there's a bunch of different ways we could think of doing that. You could actually try to build something that's like a universal quantum computer that can run this program, it can run other programs. I can make it simulate the quantum mechanics of the universe and calculate all sorts of things that are quite hard on conventional computers these days. That would be really exciting, but people think that's going to be particularly hard. We'll talk some about the details there. You might, for this specific problem, make some custom hardwired chip, a quantum chip that's just made for factoring. Okay? If you were really concerned about internet security, banks are, governments are, then they're interested in, well, can we actually find these types of things to assess the vulnerability of our security systems? And I think maybe the most fascinating question, though, as a scientist is there something out there in the universe? We keep finding new and exotic things, new systems that have strange properties when we cool them down, or we take them to very low pressure, or we look in very extreme conditions. Can we find a system that does this sort of thing naturally? I think that's the most exciting possibility of them all. So when I talk about a quantum computer, I'm talking very broadly about all of these different possibilities of thinking about a system as being like a quantum device that can do information processing. It might be a computer that looks on the surface a bit like the one on your desk, but I also might be talking about, what about the whole universe as a computer, as an information processing device? I mean it in a very general sense when I'm talking about computers. Okay, so I'm gonna skip this. Basically, there are implications of this for our understanding of cryptography and the security of systems. But from a scientific point of view, the idea of, well, what is a quantum computer? What would it be like if I built it? Here's a very specific realization of this idea of Schrodinger's cat. Schrodinger's cat was this weird hypothetical chain of events where we went from quantum mechanics of a single particle, which seems normal to us and is very well understood and explained, and amplifying those quantum mechanical effects up to the everyday scale and talking about a cat being alive or dead. And that's where it became hard to think about, almost nonsensical. A quantum computer would essentially do the same thing. It would take as our input, well, we put some atoms or some electrons or something like that in a specific quantum state, and then we start manipulating them quantum mechanically. But there's going to be a lot of these atoms, a huge number. As many atoms we're going to manipulate here as there are bits in your computer, which is billions, trillions at the moment. And we can start to think about this thing as being a macroscopic quantum system like this Schrodinger's cat, but that was just a thought experiment. Now we're actually making something like this. That's the hope. We're not there yet, but we want to pursue this goal. I just want to touch briefly on this question. I said I don't know the answer. People want to say, why does this work? Why does a quantum computer let you compute things in ways that a regular computer can't? People have proposed different ideas for it, and one of them is this idea of this quantum superposition, because that atom can have decayed or not decayed at the same time. It's both. That cat can be alive and dead at the same time. In some sense, it's both. In some weird sense, we have trouble pinning down precisely. You might say, well, a quantum computer that can be in this weird quantum superposition that can have many possible states at once. People think of this idea of a quantum parallelism, that instead of having to try the problem over and over again with many different instances, what if we could get the computer to calculate all possible instances at the same time? It's doing all the problems at once in one go. Okay? That sounds like an appealing sort of solution if that's the way a quantum computer actually works, but we don't know if that actually makes sense. That's just an idea. Another proposed idea is just if we look at the space that quantum systems live in, relative parameter space, relative to the size of their classical descriptions in the language of Newton. It's an enormous space. There's so many more possibilities for the way that a particle can be quantum mechanically than classically. Maybe this huge space serves as a bit of a sketch pad, a huge sketch pad where we can draw out much bigger solutions than we could classically. People think that this odd idea of entanglement might have something to do with it. But we really don't understand what is making quantum computers more powerful. We have instances where they can provably do much better, but we want to understand that in more general ways. Okay, so let's move on to a bit more of the physics to say, well, let's try to pursue this goal. Let's say, can we make such a device, and how would we do that? What are the problems? Why is it so hard? And what are the things nowadays that make us think, well, it's probably still possible? To have a useful computer, we need the analog of many different bits. Okay? It's not useful to have a 1-bit computer or a 2-bit computer. You want to have many of them and manipulate them together. Okay? So we need some analog of this thing. We need many quantum systems, but we need a couple of almost mutually exclusive conditions to be satisfied. We need, in order to keep these things quantum mechanical, we know from all of our experience with quantum mechanics, to have a system be quantum mechanical, you have to really isolate it. It has to behave on its own and not interact with all the things around it. So we need a whole bunch of isolated systems. That doesn't sound so hard. But then we have to manipulate these systems. We have to do gates on them. We have to drive the computation. And can you sort of see why these things are mutually exclusive? Think about that for a second. We don't want these things to interact with anything else, but then we want to get in there and cause them to interact. Okay? We want to be able to interact them, but in a very controlled way, not in a random way of randomly bumping into some gas molecule or some stray photon. We want to have complete control over that interaction and nothing else. And that's very hard to do. Let me give you a couple of physics examples where we sort of naturally have one but not the other. So the experimental effort here is really to find systems where we can satisfy both of these two requirements. So one example would be to use as my quantum version of the bit, where am I going to store the elementary piece of information, is a single electron. Okay, it's a single quantum particle. And how am I going to store this bit? Well, electrons, they're charged particles. They can move around. We might imagine trapping them in one spot so that they're not flying off. And they have a very odd property to them. So even though they're elementary fundamental particles, we don't think that they're composed of anything else. We don't think that they have any size or any shape to them. They're just really points in space that they spin. It's hard to imagine something spinning when it doesn't have any shape or any size. It's just a point. This is one of the weird things that quantum mechanics predicts about elementary particles, is that you can have a point that's nonetheless having some rotation to it. It's like a top, but of course we think of a top as spinning around, and you can look at a point on the outside of that top moving. You can't quite have that same picture for an electron, and we usually loosely like to think about things that way. This electron is just a really small top, and it can spin this way, or it can spin this way, okay? Or it can spin any other way. But we can use the direction of that spin to encode the information. Because the electron is charged, and that means we can manipulate it with electromagnetic fields. Okay? We can use electromagnetic fields to hold electron in a very small confined space. And we can do that in free space, but it's much easier to actually do it in a semiconductor like silicon. Okay? We can hold that electron still, and we can take its spin, and we can make that spin go this way, or move it, that spin around in any direction we want by controlling electromagnetic fields. Because it's a charged particle, it interacts strongly with electromagnetic fields. The problem is, because it's charged, it interacts with all the other electrons around it. You've probably heard an electron, it's a negative charge, and other electrons have negative charge, and things with like charges will repel each other. So they'll be all pushing away from each other, they'll all be interacting. And you don't want that because there's electrons everywhere in the universe. And that means this electron that you trap, that you want to be your isolated quantum system, is talking to every other electron in the universe. Now, there are ways of screening that and so on, but that's the problem. We can manipulate this electron, but that means it interacts with everything else. It satisfies one of those conditions, but not the other. Here's another extreme. Here's another possibility. Let's not use electrons. They're charged. They interact too much with all the other charged particles. Let's use something that's not charged. Let's use a quantum particle of light, which we call a photon. That can also be a good carrier of quantum information. So one of the advantages of photons is they don't interact with electromagnetic fields. They are electromagnetic fields, but they just pass through other electromagnetic fields, other photons. They just fly past each other without interacting. Now, they interact with matter. Of course, they can get absorbed by atoms and emitted by atoms, but we're quite good at creating vacuum. We can clear those atoms out of the way, or we can make sure that the material that they're in is not absorbing at this particular frequency. So it's very easy to isolate photons from interacting with anything else. So that's good. We can make them quite noiseless. But then we want to interact them. We want to do logic gates. We want to have the state over here, whether it's 0 or 1, our bit, and the state over here, whether it's 0 or 1, our bit on another photon. We want to do some logic, like an OR gate or something like that. And we can't do that, obviously, because they don't interact. Now, there's ways of making photons interact by using matter as some intermediary, but then that's the problem. Now we're putting in matter where we went through all this trouble to get rid of it. So we have things that are non-interacting, but that means they're hard to control. So these are the fundamental things that the fundamental barriers we hit up against when trying to think about how to build large quantum systems from scratch, that usually things tend to be one way or the other. And we want to find things that actually have some of the good properties of both and that sort of give a balance between these two. I'm actually going to skip through this just in the interest of time. Another guy at IBM, DiVincenzo, came up with a bunch of rules for what we would need in a system in order to be able to build a quantum computer out of it. Let me move on to just some implementations, some things where we think we can do this. So I gave you that example using photons, but I said they're hard to interact. But people have figured out a trick, again using some weird rules of quantum mechanics, to maybe get around this. And it was the fact that quantum measurement, when we look at a system, we affect it. We can't ever look at a quantum system without disturbing it in some way. Maybe we can make that disturbance controlled, and we know we can look at photons. We can stick them into a photodetector. We can stick them into our eye. We can observe these quantum systems, and if we do so in a very controlled way, maybe we can manipulate them. And so people have developed schemes for putting photons in fibers and then mixing them together and doing controlled measurements on them in order to cause them to interact. Another implementation is to use single atoms, either neutral atoms or ions. Ions are good because they're charged and they're easy to trap, and cause them to interact in some controlled way. What I put up here are some pictures of ion traps. So these things create particular magnetic fields that will hold these ions in place. And then we can use lasers shining on those ions to cause them to interact, to do these logic gates to drive our computation. So where's the laser? The ions, these are both two sides of a trap, and the ions would sort of sit in this gap in the middle, and by putting on voltages and so on those gates and shining lasers in that gap, we can manipulate those ions. Those sound like pretty standard things. We use known quantum systems such as photons and atoms, but we can also make some more exotic types of quantum systems. One is to use superconductors. And here's an example of where people have fabricated a particular type of superconducting material. So this experiment takes place at very cold temperatures, down below 1 Kelvin, where in this example, this particular material is aluminium, and it's superconducting down at that cold temperature. And when it's superconducting, we have special quantum particles to describe current flowing in that superconductor, and we can manipulate those quantum systems as well. And that's what goes on at these special little gates. We're zooming into one little area there and manipulating the charges that make up that superconductor. And another approach, one I suggested before, using electrons, but not in free space. Let's put them in a semiconductor where we can screen them from other charges. We can use a lot of the nice properties of semiconductors that we use to build regular computers. And let's start to think about how we can build quantum computers out of them. We can use electric charges, voltages on little metal gates, and that's what these things are here. These are just false color things. There's not actually a red gate there. A voltage on there relative to there creates little pockets, little holes there where we can trap individual electrons, which I said are spinning, and we can cause them to interact with each other in a very controlled way. And I've put up some names here of where I've got these photos from, of some of the leading places in the world that are developing these technologies. But we're pursuing basically all of these things here as well at Sydney. Okay? Using semiconductors, superconductors, photons, and atoms. All of these things are good quantum systems. All of these things have some advantages and some disadvantages compared to each other. And so everybody's trying every different approach to see how we can build up larger and larger quantum systems and how we can move forward. People are in a state of sort of friendly competition, but also collaborating to sort of see, is this system better or is this system better? We don't know yet. So it's quite an exciting time as all these different experiments are coming out. Okay, so I'm only going to talk for about 10 more minutes. And here I'm going to come down to one of the specific problems that we deal with in thinking about how to make a larger and larger quantum computer. And this is one that is a little more directly related to my own research. So this is a type of problem that I'm thinking about with my students on a more day-to-day basis. And that's quantum error correction. So we know that errors are going to happen no matter how well we isolate the system from its environment, no matter how carefully we control these quantum systems, something's going to go wrong, and we don't want the whole computation to fail every time one little bit in this computer does something wrong. So we have to start thinking about how we can do error correction in this computer and make it work robustly in the presence of noise or some faulty parts or things like that. Now when we talk about, I'm using that word classical again. When I say classical information, I mean information in the days before anybody knew anything about quantum mechanics. When it comes to computing, that was only about 10 years ago. People thought about everything in computing before quantum mechanics just in terms of zeros and ones, bits, and when they had to figure out how to make a particular bit robust against possible errors, say there's some chance that I have a bit in a state 0 and some error happens and it gets turned to 1, or it's 1 and it gets turned into 0, and I don't know which happened. How can I figure out how to build a computer where these types of errors can occur without it corrupting my data? And an obvious way is, well, use something like a redundancy code. Every time you want to write the bit 0, actually put down 3 zeros. And every time you want to write 1, put down 3 ones. And if one of those 3 bits gets corrupted, maybe flipped, or maybe even lost, that's okay. You can still figure out what was the original information you put in there. You just sort of look at what's the majority of what's left. Okay? So that's what we can do if we have classical systems, but how can we do this in a quantum world? So we can do error correction on classical systems by doing something like a majority vote, and then you correct based on, if I ever saw 001, I say that's most likely 000, it's just the last bit got changed. So let me just fix it back to 000. That involves looking at the system. In quantum mechanics, every time I look at a system, I'm going to disturb it. And that's the type of thing I don't want to have every time I correct an error to cause more errors. It would snowball. Okay? So I have to come up with ways that don't involve measurement, or at least don't directly involve measurement. And that's really, in a broad sense, what's tricky about thinking about error correction in a quantum sense. I think just in the interest of time, I'm just going to skip a few slides, even though they look really cool. And come down to a very specific example, using some ideas from physics to try to think about how we can correct errors in a system. Okay? So we're gonna take the basic idea of this redundancy code. We're going to use to encode, when we say we have a single quantum system, when we're thinking of it as being a bit, I want it as 0 or 1, or some weird both 0 and 1 at the same time, like quantum systems can do. I'm actually going to use several quantum systems in like a redundancy code. And I'm going to try to put that information amongst several quantum systems in a way that I can still correct things. So I might, thinking about things now a bit more as a physicist, say, well, a good way to get several quantum systems, say several atoms, is to think about a lattice, like a crystal. I'm, for various reasons, just happen to be working with this particular type of crystal, a lattice at the moment, with this weird pattern. And so that's why I just grabbed this figure. But think for the moment, just don't look at exactly why I picked that lattice. Just think of some lattice of quantum systems, some crystal of quantum systems that's going to encode my information redundantly. And I want to be able to come up with some way of saying, how do I recognize that an error occurred? And then I want to correct that system. So what I want to do is, again, thinking of this system physically, is I want to somehow create that system and its interactions such that when an error occurs, it looks like the system heats up. And then I just have to look at the system's temperature, and if I find that it's heated up, or if it's heated up in one particular place, I just have to cool it down again. So here's the type of thing that we do to solve the problem. It sounds a bit crazy, but it's actually a very tried and true method in physics that goes back for hundreds of years. We imagine that, well, what we need is a little guy that we call a demon to go down there. So we imagine this is not the demon, this is the error. Some errors occurred, and it's heated up the quantum system right at that point. So that's the bad guy that we want to fix. We imagine a little demon that's going to realize this thing's heated it up and slam it back down to 0 temperature. Cool it back down again with some sort of hammer. You say, okay, well, that sounds like you're just being ridiculous. But this idea of thinking about little tiny demons, the name demon even, in this physics context, comes from Maxwell, very famous physicist in the 19th century, thinking about problems in thermodynamics. He starts thinking about what if there was some little demon that's telling atoms whether they can go this way or this way in a gas and make things behave in some very non-standard way. By thinking about the behavior of such little demons or little devices, they were able to develop the rules of thermodynamics. And from that, they were able to build engines and cars and things like that. So this idea of thinking about things abstractly actually has a long history. So we were taking the same approach. We're imagining that we can put a little guy down there who can just look at the temperature and when some region's hot, just cool it down again, and that will fix the error. But then you say, okay, well, okay, you think about what that demon has to do, you think about what type of power he needs to have, and then if you want to make this a nice physics argument, you have to say, well, how could I make that little demon? And this idea of a quantum computer as just, in a very broad sense, an information processing device that we can program, that we can make do what we want. Well, if you have such a thing, you can imagine making little demons out of him. All we need here is not an actual little guy with a hammer, but we need a little piece of code in our quantum computer that's going to look at the temperature here and here and here and so on, and if it's hot, just cool it down. So we build the demons into our quantum computer to do this error correction. The problem is, if we build the demons out of our computer, they can't just perfectly correct all the errors because they themselves might have some error occur to them. So this demon has an error. He was about to measure the temperature and correct things, but you know, he gets blasted and does something stupid. So we need more demons to correct that demon. And we can construct layers of these things. We can have the guys that are correcting the logic right at the base level, and then this next level of guys are correcting these bottom level of guys, and so on. And we can, you can sort of see this number of demons is growing exponentially, but you might hope that with just a few layers, you start to get a system that the chances of, as long as the error rate's low enough, the chance that some guy will get corrected before we hit the top is basically that probability is going to go to zero as this system becomes very large. These are the type of thermodynamic arguments that we do in physics all the time. We think of how is this system going to behave as we grow this system larger and larger, and think about the physics of the probabilities of various things happening in that system as we take that very large limit. And that's the type of problem that we're working on these days, is how to construct very sensible ways of making these layers and layers of little error-correcting demons out of faulty parts that are themselves quantum systems, such that when we build up these things to larger and larger scales, they're going to be increasingly more guaranteed to work. Okay. So the final question people always have, I know you guys are going to have many questions, but I'm going to preempt one. People say, well, I don't have a quantum computer yet. When am I going to have one? You know, is Call of Duty 10 going to come on a quantum computer instead of a regular computer? Well, it's a very good question, and it's one that we've been asking in the field for a long time. And if there's one thing we've learned, it's that we're very, very bad at making these type of predictions. Physicists and scientists are all about making predictions, but when we start to try to predict where our own research is going in a few years, we're actually quite bad at it. And so people said 10 years ago that we're going to have quantum computers now. In fact, people said 10 years ago that it's only going to take 5 years to build quantum computers, and they were all wrong. And other people have said they're never going to be able to be done because of problem blah, 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 and we've managed to address those problems, and they're like, okay, well, maybe there's some other problems, and they're becoming a bit less skeptical. And the whole field is moving around somewhat chaotically as we try to move towards this goal of figuring out whether these quantum systems can be put together on a large scale. But we are moving, and this is the way that science works. We don't know exactly what the answers are going to be, or else we wouldn't really be interested in doing this type of research. We love the fact that we don't know the answers. We don't know how it's going to work out when we do it. So I can't tell you when we're going to have a quantum computer on our desks, but there's a company already now based in Vancouver in Canada that makes something that's very elementary at this point, and in fact people have big discussions about whether this really is a quantum computer or else it's just looking at things looking at regular sort of classical computing type things in the wrong way. So there's a lot of arguments about exactly what they've built, but they actually have a chip now that you can buy. It costs about like $100 million or something. But nonetheless, there's a picture of it. And it's for sale on the market. So you might even say quantum computers are here now, or they're coming very soon. And that's about all we can predict at this stage, and certainly the only bet that I'm willing to predict. And I'm just going to finish on that note. I have the pleasure of working with a whole bunch of great students, mostly PhD students, but also some undergraduate students and some more senior researchers here at Sydney. And this is a picture of our group just outside the front of this building. And on that note, I'll leave it there, and thank you very much.